in this lecture we are going to derive the complete discrete time model, large signal model. So, we will discuss first discrete time modeling in DC-DC converter that we have started in the previous lecture, and then we want to derive the complete discrete time large signal model. So, first if we take a synchronous buck converter, and this is the circuit diagram, more or less practical synchronous buck converter, then we know how to get A1 A2 matrix, and for R1 is equal to R2, then this A1 A2 matrix are same that we have discussed. Then we will get B1 B2 matrix, and if we ignore the external current load, if we ignore this part, then you will get this matrix if it is ignored. Okay. Now, so this is the diagram of this complete interval 2 sampling, and that we have discussed. How does it work? So, we will take the output voltage sample right here. So, we will take the sample somewhat earlier than actual switch turns on, because we are talking about the trailing edge modulation. So, this is under trailing edge modulation, trailing edge PWM. So, under this modulation we want to take the sample earlier than the switch is turned on, and that is why it is called interval 2, because as if we are taking the sample during the switch off time, which is mode 2. What does it do? So, we take the sample here and we will use this sample in the subsequent cycle, but this sample is used and it is this time is provided for ADC conversion time and the computational time, and then your control output, that means output of the controller is ready after this time. So, then your actual DPWM start, and here we are taking a STRK approximation of the ramp signal. So, if we ignore the effect of quantization, then how do you derive the discrete time model? So, you see we want to derive the discrete time model between two subsequent sampling point, two subsequent sampling point. So, earlier we wanted to derive point. So, earlier we want to derive between two switching point, there is no delay, but if there is a delay in the sampling, so we will take the sampling clock as a reference clock to derive the discrete time model. So, that is used for NT and N plus 1T. Now, how do you start? So, if you take this waveform, so let x of t, that means any state variable. So, what are the state variable? We know the state variable here, we have taken the inductor current and the output, sorry, capacitor voltage, and the output voltage will be C matrix time x of t, right, that we know. So, C we want to make C 0, because C is the output capacitor. To separate that notation, we are using C 0. Now, if you take this sample here, you will see the first it will undergo mode 2, and this point we are calling the state variable, at this point we are calling xn. Then at this point, what is the state variable? We will call here x1. So, this will be my x1. Then it will come to this point when the switch will change its state. So, this point we call x2. And if you see the duration, the first point will come t equal to nt, the second point will come nt plus ts, this is the duration ts, and the third point will come nt plus ts plus dn t on, that is the on state, this is the on time t on x2, and the final point, the point which will be here, that means the sampling point, that means this point we are taking this state here x1 t. So, your intermediate variables are these two are the intermediate variable, intermediate state, right. These are the intermediate states, and this is my initial state, and this is my final state. We want to write the final state in terms of initial state, and we want to substitute the intermediate state. How to start with? So, let us start t equal to nt, then it will undergo mode 2. So, this is my mode 2. Then, so duration of mode 2 is Ts, that is the duration. Then mode 1, the duration is what? it will be T1 and this is under mode 1. So, you can see it is mode 1. Then the rest duration, which is this one. What is the duration? This duration, if you different, then it will be total time, that means T minus T1 minus Ts, right. If you just subtract this, that means from this point to this point is our total time. This point to this point is my time is T. So, this point is Ts and this point is T1. So, naturally the rest of the point will be T minus T1 minus Ts. Okay. So, that means this is the model diagram, that means how the state propagates. So, the total duration, that means first serial M2, then M1, then M2. So, it will be for the duration NT to NT plus Ts, then it will be the duration between NT plus Ts to NT plus Ts plus T1 and then NT plus Ts plus T1 till the N plus 1 T. And for this mode, Xn is the initial state, X1 is the final state and the matrix corresponding to off state matrix A2 and B2. Then this mode initial state is X1, this state will become initial state and the final state is X2, and in this mode 1 it will be A1 and B1 matrix will be considered. Again this will be the initial state for the next cycle, next configuration. So, X2 is the initial state and the final state is Xn plus 1, and in this mode again it is mode 2. So, A2 and B2 matrix. So, by that way we will get, so you will get detail about this. There are different books also, you can refer to this paper. So, here we want to get the complete state. So, we know for each mode the state space solution. So, for this state it start with X1. So, you substitute here, what is the T01? So, T01 is NT, right, that is the initial time for this state, and T0 equal to Xn, that is starting value of Xn, because if you take this mode, the time start T0 from equal to NT, its starting value, right. And what is the N value? N value of this state will be NT plus Ts. So, X1 is equal to X of T. Then mode 2, this is under mode 2, and what is the duration? If you take the difference, it will be Ts, and during mode 2 of a buck converter there is no input voltage is disconnected. So, your solution is simply A into Ts, because we know this solution. If you substitute total T, what is total T? T equal to NT plus Ts and T0 equal to NT. So, then difference is Ts. This one will be Xn that we have defined, and since B2 is 0, so it will be simply this solution. Next, for the mode 2, again you substitute. Here what is the initial state? Is my NT plus Ts. So, NT plus Ts and the state is X1, and the final state NT plus Ts plus T1 and the state is X2. So, what is this difference? This difference will be simply T1. So, it will be T1 and the initial state here will be X1 for this mode and the final state is X2, and this state of a buck converter, your now input voltage is connected, it is beyond matrix. So, you will write this, and again the solution here, this invertible AQ, that means A1 is invertible, and here for a buck we know that A1 equal to AT equal to A we have taken. So, here we will get the solution. Next, for the third mode we will substitute. What is the initial value? It is X2. What is the initial time? NT plus Ts plus T1. What is the final time? N plus 1 T. So, what is the difference? It will be T, that means if you subtract, it will be T minus T1 minus Ts, and during this state X2 is the initial state, Xn plus 1 is the final state for this mode, and again it is the off state of a buck converter where the input voltage is disconnected. So, there will be no solution here. So, it is 0, right. So, now if you combine together mode 2, that means how it is propagated. So, your propagation is Xn propagated to X1, it is here. Then mode 1, X1 propagates to X2, it is coming like this. Then mode 2, x2 propagates to xn plus 1. So, we will get xn plus 1 with detail, and you can get detailed process in this paper. So, the complete solution xn plus 1, if you propagate, that means you will back propagate. So, first you start with eliminate x1 x2 to obtain xn plus 1 in terms of xn. So, mode 2 we know x1 and x2 also you know. Now, you substitute, that means this x1 you substitute here, and then it will be in terms of x2, and the x2 term x2 you substitute here, sorry. So, in this case it will be in terms of xn, and you substitute x2, since x1 is already replaced. So, the whole term will be in terms of xn. So, you will get the complete discrete time model like this, and you see for all these three cases it will be product, that means e to the power a ts into e to the power a tion into e to the power a t minus tion minus ts. So, since all A matrices are identical, so you can simply write e to the power, that means e to the power ts plus tion plus t minus tion minus ts. So, it will be e to the power a t, that is it. But if A1, A2 matrices are different, that means can you always write e to the power A1 T1 into e to the power AT T2 will not be equal to e to the power A1 T1 plus A2 T2 if A1 A2 is not equal to A2 A1. If we can show, that means commutative property, if they are not equal then we cannot write, but if the matrix is identical then there is no problem. So, x a square. So, here since in this case is very straightforward for buck converter, you can very easily get, but you will get a different scenario for a boost converter when A1 A2 matrices are different, then this property cannot be satisfied. So, you cannot write like this. So, then you have to write in product. So, the complete discrete time model for a buck converter can be derived by this method, and the complete discrete time model, and we will take this complete discrete time model as a vector function, because this xn plus 1, it is basically a vector consisting of ILN plus 1 and VCN plus 1. So, naturally this one will be vector consisting of F1 and F2. Why we are writing? Because we want to show this, the large signal model can be used to derive the discrete time small signal model using Jacobian approach. Okay. So, right now I am just representing this in the complete like a vector form. So, this will be a 2 cross 1 matrix, because there are only 2 states, and you will find this matrix will be 2 cross 2, again this will be 2 cross 2 matrix, and B matrix is 2 cross 1, input is 1 cross 1, and this whole term again 2 cross 2, this will be also 2 cross 2. So, we will use this vector function to derive discrete time small signal model in a subsequent lecture. So, you will get detail about this, how this vector function can be used for deriving discrete time small signal model straight by mathematically, and that can be used for for buck, boost, as well as it can be used for constant on time modulation, constant off time modulation, then trailing edge modulation, leading edge modulation, and all the derivation of small signal models are summarized in this paper. So, for detail you can refer to this paper. So, in summary, we have discussed discrete time modeling in DC-DC converters. Then we have discussed derivation of discrete time large signal models. So, here we have shown only a buck converter, but as we move forward for stability analysis, we can also do for a boost converter, because we already know the method. So, I think this is enough for today. We want to stop it here. Thank you very much.